today we're going to do section 3.8, implicit differentiation, which is on page 309. Now, we have already done a little bit of implicit differentiation in the previous section when we were proving the inverse function, but now we're going to do it officially. And it's something that you already know how to do, but it's still fun to check out some examples. The reason for doing implicit differentiation is because sometimes the function isn't so obvious. You have to, that is, the function is buried. To see an example of that, let's look at something like, well, let's go to some example. Example 3.68. That's 2 pages later, 311. Okay, let's look at the example 3.68. And we'll look at a circle. So this is example 3.68, which is on page 311, where we have a circle. Now you might remember this when you have x squared plus y squared equal to something, 25. That is a circle where I'll write down the circle formula: x squared plus y squared equal to r squared, where r is the radius. D-I-U-S. All right. Yeah, that spells radius. I hope you can understand it. Anyway, so that this is a circle with a radius of 5 units. And you're supposed to find dy by dx. That is the derivative of y with respect to x. And how do we do that? You do so-called implicit differentiation, which means you take the derivative of both sides and then see if something comes out of it. What you do then is both sides you're taking the derivative with respect to x. So this becomes, by the power rule, 2x, all right? And plus, how do you do that? That you use the chain rule, which is 2y. You don't know what y is. All right, so you will simply write it down, and then by the chain rule you have to do the derivative of dy by dx. Since you don't know what y is, you can only write this down. You can't go any farther than that. But that's what we're going to do. And this equal to 0 because that's a number. All derivative of numbers are 0. And then then we are going to isolate dy by dx. So to isolate it, we have dy by dx. And then move the 2x to the other side, becomes negative. And then move the 2y down below 2y, which gives you negative x over y. Now that is the derivative that we've been looking for, dy by dx. Notice the derivative is expressed in terms of both x and y, whereas so far we've been doing derivatives where there's x only. And that's okay. There's a reason for that, mostly because mostly because the y has this isn't a function. See, the y is buried in this stuff, and if you dig it out, in this case you can, it will be, you have a positive and a negative because it's a circle. Yeah, that's all I want to say about that. The details are not that important. The point is the derivative is expressed with both x and y. Now to see more of what this means, let's look at something else. Let's do something else. Okay, the next example, example 3.69. Which is on the following page, page 312. Let's look at, this is a very similar problem, okay? Although we might have to do a bit more algebra, it looks. Doesn't matter. Let's look at some random equation with y buried inside. So you can't just call it f of x equal to something, because the y is stuck in there and you can't get it out. Look at the equation, which is x to the power 3 sine of y plus y equals to 4x plus 3. Okay, again, we're trying to find dy by dx. Now, not possible to yank y out of here and write this equation as y equals to something like a normal neat equation. This is so to take the, but even then you can still take the derivative. And what's more interesting is that it's not that hard. You just beat it on both sides and see what comes out. So let's do that. And right now you have a product here, so we will use the product rule on this part of the story, which is take the derivative of this one first. Okay, 3x squared times the second term, we keep it, okay, by the product rule, times the first term. Okay, we take the derivative of each term one time, and times the derivative of the second term, which is cosine of y. And then right now it's because we don't know what y is, and we're taking derivative with respect to x. So when you get to y, that is you have to apply the chain rule, which you have to then take the derivative of y itself, which becomes dy by dx. All right, and then next, same thing. When you we are taking the derivative of y with respect to x, so that becomes dy by dx because we don't know what y is. So we'll just write this down, and then equals to 4x, the derivative is just 4 because we're taking derivative with respect to x. It's very important to remember what we are taking derivative about. Then right now we're doing derivative with respect to x because we're looking for dy by dx, so that's what we get. Now once you get an equation here, you notice it's similar to what we just did, is that you have a dy by dx term here and another one here. So we're going to plug it out and put all the rest on the other side of the equation, like you would solve a regular equation, and then see what comes of it. So to do that, we have dy by dx times some stuff, okay, these things, all right, which will equal to 4. I'll put all the stuff that doesn't have dy by dx on the other side, just like you would solve an equation. 4 minus that stuff, yeah, just this one. 3x squared sine of y. All right. Okay, so then so then we will isolate what we supposed to multiply. That will be x cubed cosine y, and then that's just 1. All right, and then so then dy by dx equals to that divided by that, right? 4 minus 3 sine squared sine y, x cubed cosine y plus 1. And that's the end of, that's your answer, okay? I will not write down the last step, but you can see it, you know, do the regular division. And that's example 3.69. And of course, you can, if you can do the first derivative, you can even do a second one or more, but let's just stop at second for now. Right now, we don't need to do that many derivatives yet. So, so example 3.70, example x 3.70, and we'll look at the derivative of this thing again. But we are going to calculate the second derivative. That is, the second derivative is d squared y over dx squared. Pay attention to where the square goes, okay? The top square goes in front of the d, and the second square goes in front of the x. Tradition. So, so we have the same function, x squared plus y squared equals 25, which is a circle with a radius of 5. All right, we already figured out earlier that this is the dy by dx equal to that thing. Okay, so calculate it. I'll write it over here. Dy by dx equals to that thing minus x over y. Now, what is d squared y by dx squared? That's taking the derivative of this thing. Okay, so d squared, so you will take the derivative again. So this becomes d squared y by dx squared. we're taking the derivative of both sides right now. So the derivative of this is this thing by definition. Now on the other side, you have two items, and we're going to do the quotient rule because the two items in a fraction form. Now the quotient rule says the denominator, okay, times the derivative of the numerator, which is minus 1, minus the numerator times the derivative of the denominator, which is dy by dx. Because we don't know what y is, so the derivative of y with respect to x, we'll just write it down like that. All over denominator squared. That is should be the quotient rule. Now moving along, so we got this thing out, and that now we will clean it up a little bit, which is minus y. Alright, so which is minus y plus x dy by dx divided by y squared. Right? Now, let me see. Now, is that good enough? Well, pretty much, but we still have dy by dx in here, and we already know what it is. Dy by dx is this thing. So we're going to plug that back in. Okay, and then so the whole thing looks nicer. So for the purpose of looking nice, we will plug in plus x times something minus x over y, and all over y squared, and that equals to some. And then we're gonna have to do fractions. Okay, now to do fractions, then that equals to minus y squared over y. Okay, we'll get the common denominator, plus minus, oops, I'm too cramped. All right, let me move this, write it a little lower. This is way too cramped. All right, write it a little lower. So we have common denominator. You have to see, that's why I say that this kind of stuff, the beginning algebra is what makes and breaks people's calculus skills. If they get stuck here, then they're a goner. So let's hope you don't have trouble here, but if you do, then feel free to look up how to do fractions. Okay. So that is what that is, and then that becomes is that plus minus? Okay, it ends up being this. So then it becomes minus y squared minus x squared and divided by y to the power 3. Is that right? Yeah, it is exactly what the book gets. So let's assume that's correct. So you notice that to do the second derivative, if you're forced to do this, yeah, I don't remember if I made you do homework or not of the second derivative. Whatever. The point is, you just play the same trick, and then don't forget to plug in the dy by dx, because you already figured this out. See, first you calculate the first derivative, and then you calculate the second derivative. But the only difference is you got to plug in the first derivative in there somewhere. And then, of course, don't mess up the fractions or the basic algebra. Try not to mess up the basic algebra, and then you'll be just fine. Now, example 3.71 is a standard problem of finding a tangent line. With the only difference is that you have to take the derivative implicitly, which is not any harder, and then you find the derivative, which is the slope, right, at the given point. Where in the past you only need the number for the x coordinate, but now you need to plug in both x and y in your derivative formula, which is still very straightforward. And then you use your point slope formula to figure out your tangent, as you have been doing this whole time. So I am going to assign the three examples, 3.71 and 3.72 and 3.73, all as homework, because well, is fairly generic. Okay, you got to calculate the tangent, the derivative, and then do the point slope formula. And yeah, so I will not do it myself. And and the rest of the homework is also fairly straightforward, except for problem 319. Yeah. So I will go over 319 after you have finished the homework. The homework assigned for this section is on page 317, and it's number 301, 303, 305, 307, 309, 311, 315, and 319. And that should be sufficient to let you have a solid grasp of the implicit differentiation. Now the rest, please go do your homework. And when you're done, then come back and I will do 319. All right, so let's say that, where's 319? Let's say you're done with the homework now, and I will go over 319. What? Am I supposed to do 319? Give me a second. Let's see. No, I don't think I'll go over 319. It's just the only difference in 319 is that it asks you to go over find the x-intercept first, which, as you can see, I've already done. Is pretty straightforward. I don't think it's really worth mentioning. So I will simply let you do that as homework, and that's the end of this class. Now the rest of the time, I want to say something that has nothing to do with calculus or this class, but it's something that I would like you to do if you're interested. That is, when I was in school, I majored in two things, math, but I also focus on literature. I feel that literature is very good for math students to gain a complete education, so you're not just crunching numbers all the time and being logical and inhuman, so to speak. Literature, I feel that it keeps a math student more centered and become a more to remember that you're still a human being. You're not just stuck in a mess of logic, right? So the literature recommendation I want to make today is Shakespeare. And now, before you run away and say, I already did Shakespeare in high school and I couldn't take it. Well, hear me out first. All right. So the reason what I'm saying is that I don't want you to read Shakespeare itself if you're not interested. There's nothing wrong with reading it. I've read all of the Shakespearean plays, but if you're not interested, if you have done some of it and it makes you want to run away, uh, hear me out. I don't want you to read the plays themselves. What I want you to do is read the one-page summary that you can find online, well, anywhere. Because the Shakespearean plays are not long. So to know what they are talking about doesn't take much. So if you just find some one-page summary of Romeo and Juliet or Othello or whatever, that's good enough. And you say, well, and how does that help me if I read some one-page thing? That's not what I'm talking about. After you read the one page, I want you to go look for a YouTube video or get a DVD lecture series in your library, whatever, and find a professor who talks about Shakespeare, give you a Shakespeare lesson. Those lessons usually have, I don't know, maybe 20 lectures or something, where they will talk about several plays like Romeo and Juliet, Macbeth, and Hamlet, that kind of thing. Especially those three. Those three are the main ones. And the professors will give a very interesting analysis. Now, I have so far listened to 3 series of Shakespearean lectures, and they're all fantastic. The 3 professors all said something that's almost entirely different, and yet they were all super interesting. And they make the Shakespearean plays come to life. Then you realize why those plays are so important and what you are getting out of the people in there, why they are doing what they do, and why they are being human in doing what they did. And that way, you don't consider Shakespeare as just some play where everybody died. Big, ugh, it's like ew. It's not quite like that. If you listen to the professors talk about it, I've always found it to be tremendously interesting, and doesn't matter which one, actually, just whichever ones you can get a hold of. I know I at least watched one from YouTube. I mean, that professor was Can't remember his name, but he was super inspiring. He's one reason I'm doing my calculus lectures because he was great. But my point isn't to promote some professor. My point is that you should read a little bit of just the summary to know what it's about. A page or so, a couple minutes, and then listen to the professor talk about it for 2 or 3 hours. And I mean, seriously, they can talk 2 or 3 hours about some story that's that short, and make it superbly interesting. And it also reveals the human nature. Is something that I feel that every math student should spend some time on. Not as much time as you spend on calculus, but it's something that's fun to do. And it doesn't take any work. You don't have to do homework. You don't have to struggle to figure out what is the differentiation, what's the formula. There's none of that. Once you read that one page summary, you will be able to understand everything the professor says. Why Macbeth did what he did, why Hamlet killed himself, and what is exactly the situation between Romeo and Juliet, and it's all very, very awesome. So while that is not required for this class at all, it will not make your calculus better, but I feel that it will make you a more well-rounded student. And being that you are my student, I would like my students to be as well-rounded as possible.